occasionally when I get home, I get pounced by a kindergartner, so I sometimes forget to upload my lecture promptly. So if you're wondering ever where the lecture is, just ping me on Discord and I'll be reminded to upload it. So it's no worries. Just be aware of that. He is all into Mario right now, so there's a lot of Mario Odyssey that I play with him. Although currently we're working on Luigi's Mansion. So today we are actually gonna, the past 3 days have been trying to take it a bit slow, trying to get you ease you in, make sure you had plenty of time to look at the material. All right, I plan on adding due dates and the like for the next couple weeks tonight. Hopefully I get the chance. If not, I'll definitely have the chance tomorrow. But for right now, your main concern is working on lab 2. What we're going to do today is helpful for lab 2. So the first, for those of you who saw me in 1001, right, the seminar class, I was there last Friday. We were talking about math and computer science, but one thing I don't think that got fully hammered out was like, if you're in a computer science course, right? So the computer science degree, the IS&T, the data science, they all require some level of math. And I mean, degrees themselves require calculus. So the question is, how much math do you need to be a good programmer? And the answer is not that much, actually, if you focus on the fundamentals of programming. They help. Now, the reason that we emphasize math skills for like high school is because the best determinator that we have for success in computer science at the college level is actually word problems, because those basically say, here's a problem, please, try to analyze it into this abstract format so you can solve it. That's basically our best kind of equivalence here. But as far as calculus, those things are useful. They're not even, but you don't need them to be a good programmer. Possibly to be a great programmer, but to be a good programmer or a successful programmer, it's not necessary to hammer those in. In fact, we even have courses here, numerical analysis, that are in the math department that are all about us programmers not liking to do math, so we just have the computers do the math for us. The idea here is that doing things like differential equations is hard, so why don't we just estimate the answer, and the estimation's error is smaller than what the machine can hold in it. In which case, you're doing basically the same thing as solving it, because the error is so small. There's no difference between the real answer and the estimated error at that point, so might as well just estimate. But as far as like how rigorous does the math get? Today's about as rigorous as it gets, which is dealing with conversions and modular arithmetic. This is basically our first kind of hurdle. We have a couple here. Modular arithmetic is our first hurdle. Then you have for loops. Nested for loops happen to be the next one, and then functions and parameters. That's about it. If you can master those things, you've basically got a pretty good shot at this for an A. Also, the grade distribution in this class tends to be fairly A heavy. There's a lot of A's, a smattering of B's, very few C's, and very few D's and F's, because most students are, if they know they're struggling, they'll be withdrawing. That being said, with regards to F's, okay, there's only 2 ways you can get an F in this course. Only 2. The first is you don't try. You don't submit anything. You don't come to the exams. You don't try. Okay. If you try, you get a D at the bare minimum, no matter how bad it is. Okay. So keep that in mind. As far as with regards, the only other way to get an F is by cheating. That's it. So if you don't try or you cheat, those are the 2 ways to get an F. So, so with regards to what are we going to do today? Well, today we are going to go into, well, we can check modules. And if we go to my overview, we have a link to Runestone, where I say Thursday will be a longer exercise. Okay. So this one is found by going to Runestone, by going to spring 2023, Rosen, and again, scrolling all the way down to the projects, and clicking on project 3, how many handshakes? It says here, what are the skills that are required? Statements and expressions, which are the basic things we're working on right now. How to write basic programming statements and how to write expressions. So this one goes over so first off, we're going to start with the conversion problem, but then we are going to move into truly awful problems, the ones that used to be asked as Google or Microsoft interview questions, until they realized that it was not really fair questions, because if you had encountered these kind of problems before and had at least a day's worth of experience, you could give the kind of answer they wanted. And if you've never encountered these kinds of problems before, then it was completely unfair. And, you know, it didn't necessarily tell you anything about the mindset. It just told you either you had the mindset or you had encountered this kind of problem before, one of the two. So anyway, let's go ahead but today what we're going to do is making and documenting some simplifying assumptions, solving a problem by generalizing a simpler version. The lesson today is all about basically a pattern that you'll be using for the next couple of weeks, which is input, compute, output. The idea here is that we're going to ask the user for some input, get that input, and do some calculation on it. That's the compute, and then tell them what the answer is. Basically making small programs to help them with this. Like, for instance, problem 2.1 and 2.3 and 2.4 are all of that same paradigm in your lab. They ask the user to enter something and you calculate an answer. This one is, and you'll want to save and run this, is a problem that changes years into minutes. Now, this thing may sound similar to, if you think about it for a couple of seconds, it's similar to one of the problems in the lab if you've taken a look at the PDF. If you haven't, that's okay. 2.4 in the lab PDF. And again, the lab that you're going to be covering this in is tomorrow or Monday, so don't feel bad if you haven't taken a look. But the lab has the question, seconds to, given a number of seconds, please calculate the number of hours. So this might be a bit useful here. So here, given the number of years, and I'll tell you how many minutes that is. And here's what they do. Given the number of years, they do this calculation. How many days are there in the year? 365 days in a year. Okay, then we convert our days into hours, hours into minutes. So I'll just run it and I'll go over it a bit slower, okay? So for instance, if I ask it for 10 years, it will print out 10 years is 5,256,000 minutes. Okay, so how many, so the way this calculates is, let's look at statement 1. Statement 1 is just the input statement, and that comes up like this, right? As a pop-up box that's too small for you to read right here. But what it says is enter a number of years, and I'll tell you how many minutes that is, right? That's how it does. That's how we do the input on Runestone. If it's on idle, it's just going to show up something else, right? It's going to appear in your console. Then the next statement we do is that we say years is equal to int years. So as I mentioned in our lecture videos, this is line 2 is one of those weird, funky things that you can do in programming that you can't really do in other environments. So I'll just bring up the interpreter for a second, right? And the idea here is that if I say x is equal to 5, I can, or maybe count is equal to 5, if I'm counting things. If I see another thing that I'm keeping a count of, I don't have to remember that it was 5. I can say something that doesn't make sense in math, but makes perfect sense here, because remember, the equal is the assignment statement. Count is equal to count plus 1. In which cases count's value is now 6. Now, to understand this, I'm going to use the same rule that I repeat all the way through 2168, which is that the value on the right gets stored in the variable on the left. So first, to do this statement, the first thing we do is we evaluate the right statement. We evaluate the right side. we evaluate count, which is, so we figure out what was count. What did we store in count? It was 5, right? Then we add 1 to it to get 6. Okay, this becomes 6. And so we store the value of that expression in count. That overrides the previous value. It overwrites it. And so when I ask for count, I get 6. And now when I do this again, I will get 7 and so forth. But this is also useful for doing things like conversions. Count is equal to float count, which turns this into a floating point number. Make sense? And again, these are things that are covered in the textbook. If you need me, is everybody doing fine? Or because I want to make sure that people have been doing the readings that they've been supposed to be doing. So, you know, all right, great. So this converts the years into integers, because when we take it from an input, it's a string, it's words, and you can't do mathematical operations on words. So we take for line 2, that we convert that in years into a number to figure out the, and then to convert it into minutes, we basically have to break it down piece by piece. Years are made of days. Days are made of hours. Hours are made of minutes. Make sense? So we say years there's 365 days in a year. So if it was 1 year, we'd have 365 days. If there were 2 years, there'd be 730 days, I guess. Just so then that would get stored in there. So we multiply years by 365. For days, we convert that into hours, and hours, well, there's 60 minutes in an hour, so we multiply hours by 60 to get minutes. Make sense there? You just kind of convert it down. So what would I do for seconds? Seconds is equal to what? Yes. Right, minutes times 60. And then we can update this here by saying seconds. Years is seconds. Enter a number of years. So 5 years is equal to, it's a lot of seconds. Let's see. That is 157,680,000 seconds. A lot of seconds. And yet also not that many. So now here's the big question for you. How do we go about doing this the opposite direction? So we can do this. So here, change the problem above so that given the number of seconds, how can we change this into the number of years? I mean, to do that, the first thing I'd want to do is say, I'd want to delete this first off and say, given the number of seconds, and I'll give you this and give you a shot at it. Input give me seconds, I'll tell you how many years. Okay. Then the next line, of course, is convert it, because we need to convert it, is equal to int seconds. You can, and yes, I know some of you are mentally asking but not raising your hand. Yes, you can just simply put this in one line. But in the beginning, I like to make it 2 lines to not make my lines too complicated or scary. So the question is, given the number of minutes given the number of seconds, how can I convert that into minutes? Yes. Yep. Seconds is equal to seconds divided by 60, rather minutes. And I can use integer division here if I want to. It doesn't matter. Let's see, print seconds, comma, seconds is minutes, and I will share what I have. But first, I'm going to really, unfortunately, hurt y'all. So if I say 121 seconds, that will tell me that that's 2 minutes, right? Because that's, again, it's tossing out the remainder there. If I turn it into just a regular division sign, it will tell me it's 2 and a bit minutes, right? So here's my painful question, which is lab 2.4. How do we solve for hours? And I'm going to give you a hint here. We need to delete this. How do we solve for hours? Hours, minutes, seconds. So how do we just solve for hours? And that's trickier, right? Well, the idea, seconds are made up. Well, we can start at hours, right? Right there. You can say hours is equal to, right? It's equal to what? 100, and it's equal to, so there's 60 minutes in a sec, there's 60 seconds in a minute, and then 60 minutes in an hour, right? So we can divide by 60 to get the number of minutes, and then further divide by 60 to get the number of hours. So, so there's 2 approaches to do that. You can go the I don't like math, I like following the directions I have, and just simply say, okay, I'll take my number of seconds, divide it by 60. Let's toss it in parentheses. And then so that gives me the number of minutes, right? And divide that by hours. Sorry, not divide that by 60 to get hours. Okay. Again, we could just simply do this, but you'll see why I removed this in just a second. Okay. We could just do this. Minutes is equal to this. And I can say, and I can ask for 5,000 seconds, and it will tell me 5,000 seconds is equal to 1.38 hours. Right? Maybe. I don't know how many hours 0.38 is, right? So here's the actual lab 2. Given the number of seconds, print out the hours, minutes, and seconds that's equivalent to. How many? So how do we get from here to saying this? Minutes. It's a long line, unfortunately. Minutes and seconds. So how do we get to here? Okay, so given the number of seconds, how many years is that? We take the number of seconds, okay, and we divide the number of seconds by 60 to get the number of minutes, but then the number, and so we think, okay, maybe we can just do what we have here. So if I say 5,000 seconds, I can get, it says it's 1.38 hours and 83 minutes and 5,000 seconds. Well, technically, yes, those are the individual units. It's 5,000 hours is equivalent to 83.3 minutes and 1.38 hours. But what I'm asking for is, given 5,000 seconds, I want to see it's 1 hour, 23 minutes, and however many seconds are left over. Left over, that's your key word there. When I talk about stuff left over, the key word there is modulo division. We need to figure out how to work with the remainder. So that is the essence of lab 2 right there, which is that converting in this manner requires us to use modulo. Now, going from seconds to years and just getting how many years is that and nothing else, that's not too bad, right? That's actually not too bad. But going from seconds just to hours and splitting it up into the individual time units, that's actually a bit trickier because you have to use modular division. So because we can figure out, okay, hours is equal to 60 minutes, right? 60 minutes. So if we take the number of hours we have, so if we take the number of seconds we have and divide it by 60 times 60, right? 60 hours in a minute, sorry, 60 minutes an hour, and each hour is made up of 60 seconds. So to convert that, we divide twice to get the number of hours. This will give us the number of hours that are left, okay? And then modulo 60 to get the rest. So if we look at it this way, remainder. So given 5,000 seconds, that gives you 1 hour and 1,400 units. What kind of units are they? Those are seconds, because we divided, think about this for a second. There's 3,600 seconds in an hour, 60 times 60. So that 5,000 divided by 3,600, that goes into it once. That means that if we subtract 3,600 from 5,000, we are left over with 1,400 seconds. Those 1,400 seconds are now what we can convert into minutes to get the remaining minutes. That is what I'll give you for lab 2 to get started with. That's actually most of it right there. I'll share it with you. But let's go back to the original problem, which is, given the number of seconds, how many years is that? Now, we don't need to worry about any of this modular nonsense. We can go back to what I was doing earlier, which is this, converting seconds into minutes. And asking 5,000 seconds is there. And don't worry if you didn't jot that down. I shared it with you. If you reload the page, it'll be there as one of the code points, as one of these things in your history. So how do we go for? So here, what I want to figure out is given the number of seconds, give me just years, not how many, like years, days, minutes, just years. Tell me how many years that is. So I'll give you about 5 minutes to do that on your own. It's a bit of an easier problem than what I was going over. But why was I going over that? Because it's for lab 2. That's kind of the useful reference you'll have for doing lab 2. Right. And let me know if you're having any issues. I'll be walking around the classroom. Feel free to consult with people next to you. So you're using the cost. You're using the cost time. Separating the variable industry. You don't like this there. You don't need. It's weird. It's like an idea about you have a variable in one of your string, you got to automatically convert it. So if you're doing it like I did up here, it will turn your variable off that. And it will put a space in between them as well. No. Does anybody need more time on this? Or everybody got it? I think it was fairly straightforward, but I'm never sure because it's hard for me to remember what being a complete newbie is, you know? So, all right. To do this, we just simply keep dividing our way up to get to years. Seconds is equal to minutes, hours is equal to minutes divided by I mean, I'll just do division, regular division, so that we don't lose any information on our way up. Hours is equal to 60. Days is equal to hours divided by 24, and years is equal to days divided by 365, although that's kind of a lie. What number is the proper number for the number of days in a year? 365 and almost 2.5. Yeah, I'm sorry, I'm being pedantic here. We'll learn about the entire amount of pedantry that goes into calendars when we go over our calendar, our date conversion exercise later. But yeah, it's a bit more than a year. Sorry, a bit more than a day extra in a year, which roughly comes down to about like it's 2.4 something, which is why you have weird rules for leap years. You do not know how leap years work. You think you do, but you do not know how leap years work. Trust me on that one. Unless you actually do know, in which case, good for you. So 5,000. So if we take 5,000, if we take a couple, let's see, 1, 2, 3, 4, 5, 6. So if I take 50 million seconds, sorry, 500 million seconds, and it says that that's that many minutes. Can't be right. Hours, seconds. So let's see, save and run. Give me this. Oh, right, because I'm printing out minutes. Very common mistake there that I did notice. But hey. All right, so 5. And then I promptly ignored it. So 500 million seconds is roughly equal to 15.85 years. All right. Now, part 3 over here again, enhance part 2 so that you print the number of years, months, days, and minutes. That's part of lab 2, but you're just doing hours, you know, seconds to hours, days, sorry, seconds to hours, minutes, seconds. So I'll leave that for you to lab 2, but I've already given you a head start on that. So now to get into the bulk of this. So there was this, so this is the kind of question that might get asked as a basic screening question, whereas this is one of those fun ones that I like, the unfair ones, which is something like this. How many trees are in the state of Washington? And the answer here is, well, obviously nobody knows, because I don't think anybody's actually been paid to go out and literally count every single tree. Yeah, and by the way, it's state of Washington, not Washington, D.C., because that makes a huge difference. But the idea here is estimating. All right. So, and there, if you're not familiar with the webcomic XKCD, Randall Munroe, the artist who does that comic, likes to address some of these kind of questions in his What If blog, such as, if all of digital data was stored on punch cards, how big would Google's data warehouse be? And he answers these kind of questions by making assumptions about the questions, and then turning his assumptions into into reasonable guesses. So points out that, Google probably stores, and this was written maybe, let's see when it was written. I don't know when it was written, but it was written a while ago, maybe a decade ago, but it's still probably fairly up to date. Google almost has more data storage than anybody else does. But they're secretive about their operations, so it's hard to say for sure. There's only a handful of organizations who might plausibly have more storage capacity than Google. Short list of those people are the NSA, the NRO, CIA, Schulenberger, Tencent, Chevron, Tencent. So one of these, though, interesting to note. Anybody know what the NRO is? No. National Reconnaissance Office, and you'll be forgiven for not knowing that organization even exists, because officially they did not until the 90s. They were their existence was classified until, I think, the 90s. They handle satellite data. Hence the name Above and Beyond, or hence the motto Above and Beyond. Pretty interesting. All right, so Amazon, Facebook. Amazon might have more at this point, but we'll see. But anyway, with Google, what he proposes doing to figure out what that is that they have, they look at he looks at how much they spend on building stuff. It says they've got about 12 billion. They spent about $12 billion total to build stuff. The biggest data centers cost about $500 million to $1 billion, so they can't have more than 20. And they acknowledge that they have 13 data center sites, and they appear to operate some other ones. So the idea here is that he proposes figuring out how much storage they have based on how much power they draw. They mentioned in 2010 they drew about 258 megawatts of power. And so he just simply goes down, makes some calculations there, and comes down to that it's about 215 watts per server. And each server holds so much data, maybe a terabyte or so. He said, okay, he makes the assumption 2 terabytes. And so he does that kind of calculation, and he says it comes down to about 10 exabytes of storage capacity. And now that he figures out how much data that Google can store, he can now convert that into punch cards. Punch cards, a punch card, let's see. A punch card holds about 80,000. So Google has 15 exabytes, which is that many. That's a lot. And a punch card can hold 80 characters, which isn't that much, about a byte each. And each box of cards hold about 2,000. So 15 exabytes of punch card would be enough to cover my home region, New England, to a depth of about 4.5 kilometers. That's 3 times deeper than the ice sheets that covered the region during the last advance of the glaciers. But the reason I bring this up is that they find out that the best trick for locating secret Google facilities might be the one revealed by an ex-Googler. The easiest way to find manned Google data centers is to ask taxi drivers and pizza delivery people, because they will have to, make those pizza deliveries at some point. So for how many trees in the state of Washington? How in the world do you figure that out? So this is what I want you to try to work on for the next couple minutes, and then we'll share some answers, okay? So his hint is you might want to start by looking at a satellite view of the state, okay, to figure that out. So go ahead and start talking with people and try to figure that problem out. Try to come up with an answer. Doesn't have to be a good answer, it doesn't have to be close to the real answer. I just wanted, this thing is all about how in the world do you solve big problems like this? How in the world do you address kind of questions like figuring out how many trees are in the state of Washington? And I'll go ahead, and for those of you who are not familiar, I will pull up the state of Washington. Let me go into private mode so that I don't dox my my home address and stuff. Not that it's probably hard to find or anything. It's just like, why make things easier? So let's go ahead and type in Washington state. So Washington. And there we go. There's the state of Washington, and we see a lot of green. In fact, let me go ahead and turn that into a satellite view for you. That's a heck of a lot of green. Okay, plus some weird border stuff going on with Canada, but you can ignore that. That's kind of error over there. Okay, so go ahead and use, work with people around you. Take maybe 7 to 10 minutes on this one. Work with the people around you and try to figure out how many trees are in the state of Washington. Yes. Okay, you've got Western and Eastern kind of, what I did for my answers, I looked about like how much of it is forest. And then figured out how much is, per acre. That was my opinion, but there's lots of reasons for that. I mean, you can, but trees per acre. There's no more answer. We count all the green area and the brown area. It's still and then
I don't feel like we did wrong, like this is like. Oh, yeah.
Let me just kind of tell people about that. So that's where it's at. Slide in later and finish it out. Work with somebody else to kind of figure it out, but we're not recording later. So just a heads up for everybody. You may not be aware it, but this room has access for power slots for basically every chair you're sitting in, right beneath your feet, like in that black bar right beneath the chairs. That's got power plugs in it. I've been there, wondering where in the world are the plugs? Is my battery going to last? What's the number now? Is it billion, 10 billion, 300 million? So. Well, billion is not. Billion is not right. Alright. So, I see it from like, that's, how many acres, okay, acres and then, yeah. These are rated for presentation, not for correction. All right. So why don't we take a minute and just kind of just work on this together. So, all right. So as a guest, does anybody want to share how they got their answer? I know everybody's shy, but
I started with the average amount of trees per acre, and then I looked up the acreage of the entire state of Washington.
right. So in case you couldn't hear, he said, all right, how many trees are there in an acre? How many acres are in Washington? Multiply, boom, done. Okay. So for me, anybody else do something different? Yes. Uh-huh. So working off the diameter square feet. So what was the kind of order of magnitude you had? Was it billions, was it billions, hundreds of millions, tens of billions? Okay. Well, what about you? 122 billion. That's a lot of trees. Yes.
7.7 billion.
7.7 billion. How'd you get to that?
Well, I found out how many trees Washington requires to be planted in western and eastern Washington, the amount of square feet that Washington makes up, how much an acre is. I turned the square feet into acres with the average of the trees that Washington requires.
Right. So you looked up the official source from the official sources. What is the average number of trees in the western state versus the eastern state? Because those have very different things. I'm repeating because the recording won't be able to hear you. And then you figured out the acreage per the feet, converted that to acres, and again did more conversions to get to there. But you started by figuring out, okay, what's the number of square feet and how much for the west? 190 per square foot per acre,
And then 150.
and then 150 in eastern Washington, because it still has plenty of trees over here, and this area does have trees. It's just not as many. I mean, you can see here that this looks like farmland. So, all right, anybody else? I mean, my way of doing it, by the way, was kind of eyeballing it, which is, okay, how big is the state of Washington? Washington, and everybody and for some reason we use this weird unit acres. So num acres. So let's see, land mass, Washington is 71,303 miles, or about 46 million acres. Okay, great. And how much of that is forest? Because that's where most of it is. I mean, eyeballing it, I'd say like 50% of it, right? Ish. Like half of that, it looks like forest to me. Like that dense green foliage and stuff. He's even got names like Olympic National Forest. It's definitely forest. So what I do there is I simply would say, okay, we have how many acres? I would say 46 million acres. So acres is equal to 46,000,000. And then num how many trees in an acre of forest? And yeah, that doesn't include the other stuff, but about 40 to 60 trees per an acre. So let's go with 60 because we've got let's go with 60 because because that high end might help account for the fact that I didn't count the trees in half the state. Trees per acre equal to 60, and then print. And that gives me about, so it gives me tens of thousands. It gives me about 2.7 billion. Right. So so how many trees in Washington state? And if we Google that, it's going to estimate around 5 billion. So, but again, they're working off their own estimate. You know, they make their own assumptions from gotreequotes.com. Okay. Does Washington have a lot of trees? Yes. How many trees exist? This source from the USDA, the Forestry Service, they say 9.4 billion. So if you got an answer in the billions, you pretty much hit a very good, that was a very good estimate. If you got it tens of billions, if you were in tens versus 20s, probably not too much. And if you were in the high hundreds of billions, the hundreds of millions, that wasn't necessarily too far off. So the idea here for these is just to kind of get into the right order of magnitude, just to have the right number of zeros. These kind of questions are the kind of absurd questions, but now that you have an idea about how to solve them, which is you just make wild guesses based on that. For instance, one question is like, how much does the Empire State Building, does the Empire State Building weigh? One way is, well, okay, so how many cars are in there? How many cars could it fit? And how heavy is a modern car? Are the heaviest cars? That's one way to do it. Or figure out how many houses is that equivalent to, and how heavy are the houses? Or how heavy is the block of cement? And then how many blocks of cement is that? Other questions like that is stuff like, let's see. It doesn't say it here, but like, how many gallons of water flow through the Mississippi Delta leave through the Mississippi Delta every day? One's a bit tough. It's a very big delta. But these kind of questions are these kind of interesting ones. But again, and I should mention that as long as you put something in and ran it, you'll get credit for it, because it's this exercise is being graded on completion. Sorry, on completion, not necessarily on accuracy. So so now we'll do one last one, and then if we have time left, I'll direct us to something else. So how many handshakes? So here's one good question, which is, how many handshakes would it take for everyone in your class to shake hands with everybody else? This wasn't necessarily the greatest question to ask in the middle of the pandemic, but now it's less of an issue. So the idea here is the rules are you don't shake hands with anybody twice, and you don't shake your own hand. So the idea is basically start small here and figure out patterns, right? I actually had an interview question from Google at one point that was something like this, which was like, it was similar to this, but given a game pieces that had so many, parts on them, abstract it to how many, abstract it to n parts as opposed to like the 7 that were on there, and how many pieces would be required. So these kind of questions are fairly good. So what if the class is only 2 people? If it was only 2 people, that's 1 handshake, right? So I'll start, right? If we had 2 people, Alice and Bob, they'd have to shake their hand. They'd have to make one handshake. If there were 3 people in the class, Alice, Bob, Carl, Alice and Bob shake hands, and then they both shake hands. Sorry, Alice and Bob, Alice and Carl, and Bob and Carl. So 3. Now for our 4th one. All right. So we have 4 people. You add Dan to the mix. Now we know what it's for basically. So let me go ahead and write this down. We have Alice, Bob, and Carl. We already know that they have each shaken hands. There are 3. They've made 3 handshakes so far. So once we add Dan to the mix, we can take what we know, which is that this was 3 handshakes, and now say 1, 2, 3 handshakes have to be made, right? So over here, that means that we have another 3 handshakes, so that's a grand total of 6. If we add 5, if we add an Edgar to this, or an Emily, doesn't really matter. I'm just using E. We have 4 more handshakes that need to be made, right? A, B, C, and D have to make a handshake with E, right? 1, 2, 3, 4. This is quickly becoming really messy. So 5 people means 10 handshakes. How many would 6 require? Require about 15. All right, so the pattern seems to be basically that to figure out the next number. And if we look at this pattern, we start with 1. 2 people required 1, 3 people required 3, 4 people required 6. So to get to this number, we basically added these 2 numbers together. And that pattern holds. To get to 7 handshakes, that would require 21 handshakes being done. 8 would require 28 handshakes. And so on and so forth. Now, so the question is, how do we, the question is, can you make a formula out of this? Can you figure this out? Now, if you know how to do a for loop, because you've done stuff before, then this becomes a pretty easy problem, but you don't know a for loop. You just know how to do expressions. So go ahead and take maybe a couple minutes to try to figure this one out, to try to say, how many handshakes are there? All right. Let's see. So has anybody figured out a formula yet? Yes.
I did the total students in class in variable, and then I had the number of handshakes each student has to do from the total number of students minus one, and then I multiplied the total number of students by the number of handshakes.
Okay. So six students get you what? 30, according to that, unless you're missing something else.
Yeah,
30. Very close, because what you want is 15. Yes,
Do what he did with divide.
yeah, but divide by 2, right? So I'm just wondering, how did you get to that? To do the multiplying?
how did I get to it?
Yeah.
I just figured that you need, the total number of students, and each student has to shake each other's hands, but not their own hand. So you just be doing shaking everyone's hand once beside yourself, so you subtract yourself from the total. And then each student has to do that, so you can find it.
Okay, so I'll be upfront with y'all. I know what the answer is because I'm awful and I spent way too much time in math. But I don't know how you're supposed to get there because I just know it. I know that this is this is simply triangular numbers. Yes. So triangular numbers are very, and I know that because triangular numbers plague me. They plague this class. Triangular numbers are of the format of 1 plus 2 plus 3 plus 4 ... all the way to n. Okay. And that is equal to n times n plus 1 over 2. How are you supposed to know this? We learned this in Calc 2. It's awful. By the way, this is not to be confused with 1 plus 2 plus 3 plus 4 all the way up to infinity, which is equal to like what, -1/12, like -1/12 or something. It's weird. Math gets very weird at the extreme. Except that's, totally a lie that I just said, but also not really. Triangular numbers are called this because they look something like this. Sorry, actually, why am I making an awful drawing when I could just go to Wikipedia and show you a much superior drawing? So triangular numbers look like this. And it is what they look like is the reason we call them that. The first triangular number is 1. The second triangular number is 3. The third is 6. The fourth is 10. So you add a layer each time, right? The first pair makes 1 handshake. The second pair makes 2. The third makes 3. The fourth makes 4. And then you just count up the number of dots because we can just keep arranging them in triangles. That's why they're called triangular numbers. It's a weird thing. And again, the formula is this, which is you just simply add them all up and you get n times n plus 1 over 2. And then let's see. So in triangular numbers, solve the handshake problem of counting the handshakes of a room with n plus 1 people. Now, the reason why this works, visually speaking, is very close to what was being said, which is that given. So let me go ahead and get somewhere a bit clear. So given a number of people, right? So say you have n people, right? This is a column of n by n people, right? People don't, first off, people don't shake their own hands. So this person doesn't shake his hand. So here's this column. So basically, this is basically a column of like, here's all n people, here's the same n people, right? Just simply split into rows and columns, same people, right? One person doesn't shake, you don't shake your own hand, and also you make sure you don't repeat handshakes. So for instance, this person won't shake his own hand, and he'll also shake hands with, and he's shaking hands with everybody else. So this works. But if we go down this column, then that gets us repeats. So repeat the same thing over and over again. And you get basically, well, essentially a triangle. Oh, not quite all of a triangle. And that's where the divided 2 comes by, because what you're doing, and that is where the divided 2 comes by the way. So the logic that was being used here was that, right, you got num people, right? So say num people is equal to 5, okay? Num handshakes is equal to num people times num people minus 1, because of course, for every person, they need to shake hands with every other person. And you don't shake your own hand, and you don't shake your own hand, right? That's where the minus 1 comes from in. You don't shake your own hand, right? Because if it was num people times num people, that would be everybody, it would be everybody shaking everybody else's hand and their own hand. Make sense? Minus 1 to not shake your own hand. Now, where in the world does the divided by 2 come in? Well, simply put, if we're saying, okay, Alice, shake hands with, so Alice, Bob, Carl. Let me go ahead and scroll down. So we've got Alice, Bob, and Carl. We've got Alice, Bob, and Carl. Alice won't shake hands with herself. Neither will Bob, neither will Carl. Alice will shake hands with Bob and Carl. But over here, we see that when we get to Bob, Bob has already shaken hands with Alice. So we don't need to shake hands again with Alice, right? That'd be repeat. Same over here with Carl. Carl doesn't need to shake hands with Bob because Bob will have already shaken his hand. Make sense? So that's where the divided 2 comes in, because half of this, because we don't need this, all of this grid, we just need half of it. Divide by 2 gets rid of our repeats for us. And so print num handshakes is equal to, well, this will be division because it should be a whole number. So with 5 people, that's going to give us 10. Let's go ahead and do int input num people, right? And if we now run this, we can put in the number of people, such as if we had 150 people in class today, that would take us 11,175 handshakes. A lot of handshakes to get to each other. So everybody kind of understand this? As I mentioned, these aren't the kind of questions I'll be asking. Now, I should be clear. These aren't the kinds of questions I'll ask during exams. The questions I ask during exams are more fundamental, more along the lines of, on the first exam, you'll definitely have, so in the next couple of weeks, we're going to learn turtles in more depth. And I'll typically do things like, here's a turtle. Here's a bunch of commands for turtles. Please draw what this does. Here's a computer program that runs a turtle. Please draw on your paper what it does. Or something along the lines of, here's the output of a turtle program. Please give me something that draws this, right? Lots of ways to do that one. Or even sometimes, hey, here's a partially completed turtle program, and here is the end state. Please add the missing code in, right? Things like that are kind of what I do. So not necessarily weird stuff that require math and gives advantage to people who've already taken calculus, Now, that's not the kind of thing I do. But this one, it's kind of interesting to look at these kind of problems and how you can split them up. And you can get to the same answer by following logic. All right, so now before we end class for the day, all right, I want to just point, so you may have gotten an announcement today. Let's see, for research project participation. All right, our university and University of North Carolina, Charlotte, we're doing a survey. There is a survey below. I don't give any extra credit for doing this survey. It's not required or anything, but if you do take the time to fill it out, it will be extremely helpful for us. So I will mention more about it maybe on Monday, but if you have the chance to take the survey, it's voluntary, confidential. I won't know who took it. I won't know what, and I won't know what you put in. But it will be a great, I would consider it a great help if you did fill out that survey. All right. So with that, I'll be here if you have questions, demos, and the like. On next week, what we're gonna do is we'll start working on turtles and importing libraries, and then beyond the and start our first approach on for loops.
So the lecture session recorded so I can come back and.
Yep, and I'm actually hitting the stop share right now, and the